How are you, everybody who is watching this video? I would like to take this opportunity to welcome some physical students who are pursuing electronics and telecommunication engineering into this interesting class of learning about power electronics. Similarly, I would like to take this opportunity to welcome online students to join us in the process of learning about power electronics. If the first time to meet me, my name is Olenjolai. I thank God that I will be teaching you and also I'll be engineering into your mindset. I would like to tell you that in advance, welcome into departments of electronics engineering. We are teaching a number of modules in that department. One of the modules is the one that's called the power electronics, and we have a number of chapters in this module. The second chapter is called the power electronics devices, and we are in lecture 4, brief descriptions of power electronics devices. This is very interesting. It's another branch, it's a special branch of electronics engineering where actually we discuss semiconductor from another aspect, and especially from the aspects of the power. And when we talk about the aspects of the power, we mean about the aspects of the controlling and conversions of electrical power. So this course is actually dedicated to the beginner students and also even intermediate students who are pursuing ordinary diploma in electronics engineering or telecommunication engineering or electrical engineering or biomedical equipment engineering or mechatronics engineering and even computer engineering. So it's a very interesting course also for undergraduate or bachelor degree students who are pursuing electronics engineering, telecommunication engineering, electronic science. It's a very important course because it's one of the branch of electronics engineering, and it has a number of real-life applications. So I'm just trying to give you introductions to see the importance of the subject. You might be just waiting to start the class, but maybe you don't know where you're going to apply this knowledge. So the innovations or the inventions of power electronics made a great changes in the technology, especially modern electronics engineering. So I would like to ask you that to concentrate, be serious. We're extremely serious in this course, and we ask you to write. This is not a movie and this is not a cinema. It's a lecture class. I give you a promise that I'm going to teach you more than lecturing, because there's a difference between lecturing and teaching. So I'm going to teach you, however, that I wrote lecture 4. So it's just the name of the lecture. And I would like just to invite you to ask questions when we'll be continue with the class or with the lecture 4. Or sometimes you may ask questions at the end of the lecture. I'll be happy to hear a number of questions from you, and we are always learning. So there's nobody who we call it a master of power electronics. Power electronics is changing year after year. You might be a master of power electronics in 2025, but 2030, it means 2030, you might be completely outdated. The power electronics that you know is no longer used in the real world scenarios. So I believe that you are ready, and let us go directly to the class. But this is a precaution I always give to my students, I don't know everything about power electronics, I just know a small portion. I am a student of power electronics for the rest of my life, but I have a responsibility to teach others about what I know. So regardless that I'll teach you 20 lectures or 30 lectures, it doesn't mean that I know everything about power electronics. I just know a small portion of knowledge, understanding, and wisdom or applications of power electronics. How are you, electronics and telecommunication engineering students?
We are fine.
How are you again?
We are fine.
Well, Happy New Year 2025. Thank you. Are you ready for lecture 4?
Yes.
Are you ready for lecture 4?
Yes.
Well, so let us start with quick review. So before lecture 4, we covered or we learned a lecture called the lecture number 3 or lecture 3. And actually the title of this lecture is what? Brief description. Say brief description.
Brief description.
So brief descriptions of 40 different actual of 3 power electronics devices. Power electronics devices. In that brief descriptions, we had a focus on 3 parts. The first part, I was actually explaining you, and I told you about one of the main function of particular power electronics device. Of particular power electronics device. And then we had a discussion about power electronics applications of that particular device. And then in this lecture, we discussed about the metal oxide semiconductor field effect transistor, aka we call it a MOSFET. Say MOSFET. Say MOSFET. And its peculiar characteristics, we say that this is a high speed electronics switch. A high speed electronic switch. A high speed electronic switch. Yes, and that the special characteristics make MOSFET to be used intensively in power electronics. So he said that where are we going? Where can we use MOSFET? In which system can we use MOSFET? In which power electronic system we can use MOSFET? Pardon? Pardon? Are you speaking or you are just breathing? Mention the applications of MOSFET in power electronics. So it is used in DC to DC converter. What are the other names of this DC to DC converter? Okay. Then another power electronics device that we have discussed about thyristor. Say thyristor. When we have been discussing about another issue that we have discussed, I gave you some examples. Okay? So one of the main function, and also we discussed about power electronics applications of that device, and also I gave you some examples of that particular power electronics device. So then we say that thyristors, and this one we say will focus on silicon controlled rectifier. And then we say that thyristor, it has a special switching mechanism. It has a special switching mechanism. It actually need triggering signal, and when it's turned on, it needs triggering signal to turn on and remain. It means that it remains on until the triggering signal or the currents fall below a certain threshold. Then we discussed about the SEDI power electronics device, which is called the insulated gate bipolar transistor, or IGBTs. And IGBT simply say that this is a combination of MOSFET plus BJT. So why IGBT needs the combinations of MOSFET and bipolar junction transistor or power bipolar junction transistor? You can do it further studies. In case of thyristor, I gave you 3 examples. The first one is called the silicon controlled rectifier. The second one is called the Triac. Say Triac. And then the other one is called the Diac. So that is what we have discussed. It's more than. This is just a brief descriptions about what we have discussed in lecture 3. So in lecture 4, let us continue to discuss about some other power electronics devices which have mentioned it, but we do not have description. And the importance of this topic, we don't have enough times in one semester to learn about all the power electronics devices. So that's why we are trying our level best to give you an introduction, a solid foundation, so you can go further as well as you can. Are we together? Are we together? Because, for instance, maybe you want to learn more about IGBT, at least that. In power electronics, you heard, and you knew that there is something called the insulated gate bipolar transistor. So you can go further. Okay? Okay? Yeah. So, number 7, because we've discussed the 60 power electronics devices, number 7 is called, let us discuss about silicon solid relay. Silicon solid relay. So SSR. We like abbreviations in engineering. In electronics, we like abbreviations. In telecommunication, we like abbreviation. Class say with a great power and a joy. Say silicon solid relay.
Silicon solid relay.
Again, say silicon solid relay.
Silicon solid relay.
I want to tell you that you will learn about silicon solid relays only in power electronics. You'll never find it in any other modules. So it's your decision to hear and learn briefly, then you move with your own life, it's fine. So the first question, we say that, the first question, we would like to know, what is silicon solid? What is silicon solid state relay, or SSR? So simply we say that a silicon solid state, solid relay, solid relay, we say that is a type of electronics relay that uses semiconductor components. So uses semiconductor components primary silicon based primary silicon based devices like Triac or Triacs, like thyristors, like silicon controlled relays, instead of using mechanical parts. To switch electric loads. To switch electric loads. So this is a simple definition of silicon solid relays. So a silicon solid relay is operating. This is the type of electronics relay. Say electronics relay. Say electronics relay. We have electronics relays and also we have telecommunication relays. So relay is a phenomena you'll encounter in electronics engineering, you'll encounter in electrical engineering, you'll encounter in mechanical engineering, you'll encounter in telecommunication engineering. Because relays in telecommunication engineering, we means that those are the basic transceiver stations that actually are used in between the two BTS in order to boost the signal due to the effect of the media. So, if that's the case, you say that a silicon solid state relay is the one type of the silicon relay that uses semiconductor. So this one uses semiconductor components. Primary silicon-based DOT devices like Triacs, Syristor, silicon controlled rectifiers. Instead, say instead. Say instead. Instead of using what? Mechanical parts to switch what? Electric loads. I said it's operating. So before I clarify this sentence, what does it mean and what the difference, because we heard about mechanical parts and electrical parts, let us reinforce what I've written on the blackboard. 1, 2, 3, read. Well, thank you. So we have mechanical relays. Say mechanical relays. This is that are the old relays. But also we have electrical relays. And then now we have solid state, or we have what is silicon solid relays. These are the electronics relays. So listen, a mechanical relay, this is actual, we say it's a mechanical switch that actually need the actual movement when switching. So relay is nothing. Relay is just a coil. It's just a coil and terminals. So these mechanical relays, these are the oldest relays that we had in the world. But we have electrical relays that we are still using them nowadays. The electric lift that we are taking from the ground floor to the 10th floor or to the 11th floor or maybe to the 7th floor or to the 60th floor. It uses electrical relays. Say electrical relays. So electrical relays, they have two main parts. The first part is electrical part, and the second part is mechanical part. What does it mean? Because I know that you know nothing about relay. Before I discuss about silicon solid relay, listen. Electrical relay, the schematic symbol for electric relay. I've also discussed about relay in assignment, in one of the questions of the assignment, if you do remember. So this is the coil, and this is the primary coil. We call it terminal 1, terminal 2. And this part, in most cases, called DC power source, or DC power. And then you have a bar of the magnet, okay? Or we just have, yes, we have a bar of the magnet. And with that, we say that we are going to have terminals like this. Then we are going to have another terminal like this. Then we are going to have a common terminal. So you're going to have what? A common terminal. So this is terminal number 3. Common, sorry. So common. So you say that the common terminal. So this is terminal number 3, terminal number 4, terminal number 5. This is called the normally open, and this is called the normally closed. So the intention, you have to know the schematic symbol of different electronics components. But the intention there is actual to show you the difference between electrical relays, which you call them electromechanical relays. Say electromechanical relays. I can say electromechanical relays. We have to know how they differ from the silicon solid relays. This is how they differ. So this is terminal 1, terminal 2, terminal 3, terminal 4, terminal 5. And this we call it common. You should not worry about the names of the terminals, because discussing relays, you need at least see a combinations of the theoretical simulations and practical of almost the 10 workshops. So, we say that this is the pole. Say pole. This is the pole. So this pole is actual that we say, if there is a flow of electric current in this primary circuit, then there is induced electromotive force. And that induced electromotive force actual will attract the pole, and the pole will be disconnected from the normally closed terminal into the normally open terminal. When you switch off or you turn off, class, I won't write what I'm explaining to you. When you switch off this DC part, when you switch it off, it means you switch the power off. There is no any electromagnetic field produced at this point. There is no any magnetic field produced at this point. And because there is no any magnetic field produced at this point, then what do you expect? We expect that the pole will be disconnected from the normally open and connected to the OT normally closed. That's how the principle of operation of electromechanical relay. Is it clear? Is it clear or it's not clear? Eh? I say that electromechanical relays, it depends. This is single pole, single throw. When there is a DC, or when the DC power will be flowing on these primary circuits or on the primary circuit, then there will be induced electromotive force, and this induced electromotive force will actually, because this is the electric conductor, it will attract this electric conductor, or we call it magnetic material. And when it attracts it, then the pole will be disconnected from this is normally closed, and this is common. So it will be disconnected from the normally closed, and then for that time, this pole will be moved mechanically. It will be moved mechanically from the normally closed, but that is in case we have what? We have DC source flowing through the coil. When this DC source is disconnected from the circuit, what will happen? Then the coil will be de-energized. And for that case, there's no any magnetic field holding the pole into the normally open. So if you turn it off, actually it will ask you, or after that you'll see that this relay returns to its original or resting position, which is called the normally closed. Okay? So with these electromechanical relays, you see that the primary part, or this side, the DC part, is electrical part. But these poles, the movements of this pole from normally closed, normally open, is mechanically. That's why you say that instead of using mechanical parts to switch OT, to switch the electrical loads. Because even these electromechanical switches, also we are using them to switch electric loads. Stand up. So then, What do you say? Now, the silicon solid relays, it does not use the mechanical parts. It doesn't work in this principle. I mean that the silicon solid relays is going to use semiconductors. So this relays is going to use either Triac, say Triac, or it is going to use a silicon controlled rectifier, or it's going to use thyristor. So it will be using a Triac or silicon controlled rectifier or thyristors to switch the electric loads. So it means that in this one we want to have mechanical movement, and because for this mechanical movement, when actually that you approach close to the heavy loads or heavy relays or heavy electromechanical relays, you can hear them when they make contact and when they disconnect from the contacts. So these solid state silicon solid relays, they are not using these mechanical parts. Instead, we replace this mechanical part by using semiconductor. Class, are we together? Okay. The silicon solid state relays are widely used due to their high speed, they have a very high speed switching, and also they are reliability, and ability. And the ability to handle. Ability to handle high they have high ability to handle high voltage and high current with no moving parts. High voltage and high current with no moving parts. That's another important sentence. So in this lecture, we are not going to start in detail about silicon solid relays. I'm just going to give you a brief description. Then power electronics or applications of silicon solid relays in power electronics. In which system that you expect to find the silicon solid relays. So the following are few of applications, or some of the applications of solid state relay, silicon solid relays in power electronics. Number one, we are using the SSR in switching AC. So this one, they use these applications of SSR, so that there are silicon solid relays are used to switch. So these are used to switch AC loads. Say AC loads. Class A AC loads. Who can give us example of AC load? Gideon, give us an example of any AC load that you know. Yeah? Gideon has no idea. My friend there, what's your name? David. Okay, David, give us one example of AC load that you know. No idea? Huh? You know none? Juliet, give us an example of AC load. Juliet, give us one example of AC load. Yeah? You know none? Huh? Deborah, give us one example of AC load. Jonas? The socket? No. Thank you for trying, but the response is not correct. Shukrani? No idea. Deogratias? In English? Bulb. Very good. So bulb is one example of AC load. Clap your hand for him. Huh? Clap your hand for him. Mwenye wivu ajinyonge sana. Okay, so when we say that these SSR are used to switch AC loads, we have so many examples of AC loads. We are using them domestically. Electric fan or AC fan. In most cases, you have AC fan. We have electrical iron. We have electric cooker. We have a number of them. We have refrigerator. Those are the AC loads. Do you know refrigerator? We have air condition. We have so many AC loads. We have somewhat sewing machine, drilling machine. All of them are dirty. AC. We have a television receiver. So that's one of the applications. So in case you want to switch AC loads, you may prefer to use a silicon solder relay. Okay? Class A, switching AC loads. I can say switching AC loads. So the SSRs are also used to switch DC loads. Say DC loads. Sit. Say DC loads. Astrida, give us one example of DC load or direct current load. Bulb. So do you have DC bulbs? Juliet, do you have DC bulbs? We don't have DC bulbs. Oh, you are not sure? Brother, tell us one example of DC load. What's your name? Leon. Gideon. Leon. Second one? Second name? Leonard. Okay, Leonard, Mr. Leonard, give us an example of DC load. Madam, give us an example of DC load. Solar panel. Okay, good try. Madam, what's your name? Diana. Okay, give us one example of DC load. Okay, we have so many examples of DC load. So, do you know what the means of the load first of all? When you talk about load, we don't mean about Tibuana. You have to differentiate load with this spelling and the load with this spelling. This means 1. This is load. It means that is any device that can consume or needs electric energy in order for it to work. Are we together? So how many DC? Okay, can you mention now the example of DC loads? We have so many. The first one is the bulb. We have DC bulb. In most cases, it is 12 volt. 12 volt bulb. But also you have DC motors. You have DC stepper motor. We have DC motor. You have DC servo motor. So you have a number of DC OT loads. Then the silicon solid relays can be used also in a high-speed switching system. So the SSR in power electronics can be used or are used in power electronics in high speed. So in case we have high speed switching system. So the high speed switching system. So the SSR are used in high speed switching system. Say high speed switching system. Then also the SSR is used or are used the solid or the silicon solid relays are used to control the heating what? To control the heating elements. So in case that you want to design heating elements, say heating elements. Example of heating elements are air, electric iron. The second example of heating elements is ladies. You're always heating by using heating elements. Jacqueline. The second example of heating elements is heater. Very good. Clap your hand for Jacqueline. 1, 2, 3, clap. Hongera. Imara. Wow. Answer again. Try again to answer the question for the next time. So we have 2 common heating elements that we are using in our homes. Electric irons. How many of you have electric irons? Raise up your hand, because others maybe they don't know. How many of you have electric irons? In your hostel or in your room or at ghetto? So raise up your hand if you have electric iron. Yes, do you see that? Yes, some of the teenagers here are living in ghetto. So you don't use electric iron? Okay. You are lying to electronics. Then we have also electric heaters. Those are the examples of what? Heating. So in case you want to control electric irons, you have to think about silicon solid relay. In case you want to control electric heater with high speed, then you have to think silicon solid relay. Are we together? Are we together? Okay. Then the SSR, the 5th applications of SSR in power electronics, you say that this one SSR are used in over voltage protection. Say over voltage protection. Say over voltage protection. Electric appliances sometimes suffer over voltage. So because they suffer over voltage, then you need your device to be protected. One example of a voltage over voltage protection. Stop writing. One example of over voltage protection is called the stabilizer. It's called what? Yes, if your parents are serious to protect the music system, at their sitting rooms, they always connect the electric appliance to the stabilizer. And stabilizer is the one that connected to the socket to draw electric power. Do you know stabilizer? Okay, tell your neighbor the structure. How stabilizer look like? The SSRs are used in power electronics in overcurrent protection system. So overcurrent. So in case you want to design overcurrent protection, you may need a silicon solidity relay. Are we together? Yes. So also stabilizer can protect your electric appliances from what? Over what? Okay. The seventh applications of solid state or silicon solid relay is called that the SSRs are used in phase control system. Phase control system. Say phase control system. Listen. Whenever we talk about, I say listen, stop writing. Whenever we talk about AC electric parameters, such as voltage or such as current, then we say that electric signal or electric voltage may be defined at a particular angle. And that angle, which can be used to define electric voltage or electric current, we call it phase. Okay? And I gave you a simple example of real-life applications of phase control system. I told you that we are using in power generation, transmission, and even distribution. In a high power system, we have single phase. We have single phase, and also we have three phase. So SSR can be used to control the phase. When you talk the phase, it means the angle of electric quantity. Are we together? Class, are we together? A question about silicon solid relays. If you have a question about what you've discussed in silicon solid relay, you may ask. Gideon, welcome.
My question is, how is that SSR used to control phase?
Okay, did you hear Gideon's question? Can you ask it loudly?
How is that SSR?
Jonas, did you hear Gideon's question?
How is that SSR used to control the phase system?
Jonas, did you hear? So Gideon, speak loudly.
How is that SSR is used in phase control system?
Deborah, did you hear? Deborah, did you hear Gideon's question? Diana, can you help Gideon? Ask Gideon's questions loudly. Now it's time for Diana. What did Gideon ask? Diana is praying. Say, Diana is praying. Let this cup live beside me. Mungu naomba kikombe hiki kiniepuke. Okay, Gideon asked a question. How silicon solid relay is used to control what? is used in phase control system. So who can answer that question? Deogratias, please try to answer Gideon's question. Oh, Deogratias is also praying. Safe, answer Gideon's question. You want to answer Gideon's question? No. Why? No idea. Are you sure? So this is your today's exercise book. Okay, Gideon, I cannot tell you that how the silicon solve the relays. First of all, thank you for your question. And in this lecture, I cannot tell you that in detail how the silicon solve the relays are used in phase control system. Each of these applications is the number of lecture. Right? Because you should not only discuss how is it switched, you need to draw the block diagrams for this part and also the schematic circuit diagram. Block diagrams for this use and schematic circuit diagram. Block diagram for this system and schematic circuit diagram. Block diagrams for this system and schematic circuit diagram. Block diagrams for this system and schematic circuit diagram. And then block diagrams for this system and schematic circuit diagram. Block diagram for this system and schematic circuit diagram. So in total you have 7 block diagrams and also you have 7 schematic circuit diagram. That explaining and clarifying. So that's why the title has been written brief description. Okay? Are we together? Class, are we together? Yes. But you are not limited. You can go and read how the SSR is used to control phase or in phase control system. Right? Then number 8 is called the get turn off thyristor. Say get turn off thyristor. Again loudly as electronics engineering students. Say get turn off thyristors. This is another type of thyristor, or it's another type of semiconductor device where actually you learn it only, or you learn it in power electronics only. You won't find this in analog electronics. You won't find this in digital electronics. You'll just find the beauty of this, of get turn off thyristor in power electronics. So it's your decision. You want to master it or you just want to hear it. So then we say that the get turn off thyristor, the get turn off thyristor is similar to ordinary thyristor. Is similar to ordinary thyristor. So this is similar to ordinary thyristor. But the GTOs can be tuned off. Can be tuned off. Can be tuned off. Can be tuned off by using a get signal. The GTO are unlike a regular silicon controlled rectifier. which requires current interruption. Current interruption. Say current interruption. Say current interruption. So it's require current interruption to turn off. Separating. So the two sentences are actually give you an idea concerning about T, get turned off thyristor. I say separating. So the sentence, the first sentence actually say that the gate turn off thyristor is similar. Is what? Similar to the ordinary thyristor. But the difference is the GTO can be turned off by using a gate signal. When you talk about gate, it means that you are talking about what? Field effect transistor. We are not talking about, you should not claim that whenever we talk about gate, we are talking about MOSFET. No, MOSFET is one type of full field effect transistor. Right? Right? So MOSFET is just like NPN in bipolar junction transistor. So when you talk about NPN bipolar junction transistor, we doesn't mean that we don't have PNP. No, PNP is there. Then we say that, so the difference it means that this is turned off by using gate signal. When you study in detail, you'll understand that how that gate signal is obtained and how is it used to turn off the GTO. The GTOs are unlike regular silicon controlled rectifier. That's the second sentence. Why or what the difference between the GTOs and silicon controlled rectifier? The difference is the GTO require current interruption to turn off. No, the silicon controlled rectifier require current interruption. Say current interruption. Say current interruption. So the GTOs require the gate signal or the interruption from the gate signal in order to turn off. And then silicon controlled rectifier, actually they need current interruption to turn what? To turn off. So when you talk about that, it needs gate signal in most cases, because remember that gate has a very high impedance. You learned it in analog electronics. Gate has a very high what? A very high what? In such a way that the gate allow a very small current to flow through it. For that case, that we say that whenever we talk about gate of the field effect transistor, and whenever we think about the signal which will be allowed to pass through the gate, in most cases it's the voltage. It's what? It's what? And that's why that if fate characteristics, we always draw the fate characteristics of what? By using the drain currents against a VG of voltage across gate source. So this is the gate voltage. Are we together? While in case of the bipolar junction transistor, the characteristics actually we draw the characteristics by using the collector current and the base current. So in case of bipolar junction transistor, it means the base signal, in most cases it's base current. Okay? While in case of the MOSFET, those are the differences between bipolar junction transistor and MOSFET. You have to know the difference, at least 5 differences between bipolar junction transistor and field effect transistor. Okay? So this we call the transfer characteristics of bipolar junction transistor, and this is the transfer characteristics of field effect transistor. Are we together, class? So whenever we talk about gate signal, we mean about 20 voltage. Why do we think about voltage? Because the gate terminal, it has high impedance. Say impedance. Say impedance. What is impedance? Ask your neighbor, what is impedance? Ask your neighbor whether your neighbor is seriously or happy or unhappy. Ask him a question. Define impedance. Then let us think about power electronics application. Who is speaking? Power electronics application. Power electronics application of what? GTO. Power electronics applications of GTO. So, the gate turn off thyristor are used in high power. So these are used in high power control application. High power control application. Like what? Stop writing. These GTOs are used in high power control applications, and the following is the list of 40 of applications where you can use the GTO. We are using GTO to control electric trains. In Tanzania, do you have electric trains? How many electric trains do you have? Transmitter? A Sierra. How many electric trains do we have in Tanzania? 1, 2, 4. You don't know about your own country. So the electric trains that we are using traveling from Dodoma to Dar es Salaam, or Dodoma to Morogoro, or Morogoro to Dar es Salaam, or Dar es Salaam to Dodoma, they are being controlled by gate turn-off thyristor. Then we are also using gate turn-off thyristors in controlling motor or in motor drives. Say motor drives. Say motor drivers. Say motor drivers. Say motor drivers. Also, you are using GTO to control high voltage direct current. This in electrical and electronics engineering, we call it high VDC. High voltage direct current. Say high voltage direct current.
High voltage direct current.
Again, say high voltage direct current.
High voltage direct current.
Bado. Wewe ushaongea bwana. Wewe mbona unasahau tulichoongea? Kakae bwana. Ushaongea. Muda ukifika saa 12 dakika 20 na harusi. Na nusu leo. Then the next one, number 9, is called the power capacitor or power capacitors. Power capacitors and the power inductors. Power capacitors and power inductors. Say power capacitors.
Power capacitors.
Say power inductors.
Power inductors.
So the main function of any capacitor is to store electric energy. Class, what the main function of any capacitor? Again, the main function, what the main functions of inductor? The main function of any electric inductor or any inductor is to store electric energy. So this one store electric energy by using what? Electric charges. This one store electric energy in form of electromagnetic fields. So the main function of any inductor is to store electric energy in form of electromagnetic fields or magnetic fields. Say magnetic fields. Say magnetic fields. So this is magnetic field. Let us omit this word. So magnetic field. So the inductor, the main function is to store the electric energy in form of magnetic field. And the capacitor, the main function, listen, the main function of any capacitor is to store electric energy in form of electric field. While the main functions of the inductor is to store electric energy in form of magnetic field. Remember that whenever we have a flow of electric signal, we have magnetic field and also we have electric field. And there's a relationship between magnetic field and electric field. That's why that we have a theorem say that whenever we have current, we have magnet or we have magnetic field. And whenever we have magnetic field, we have current. Do you remember that? Do you remember that? So if that the case, if that the for foundational skills about the power, about the capacitors and inductors, then the question comes, how are we using the power inductors and power capacitors? Remember that this get turn off resistors in some of the book, they might call it power get turn off resistor. The general purpose diodes that we discussed or rectifier, in some of the books they might call it power diode or power rectifier. It talks that these components or these electronics components is actual discussing about what power electronics. So then now let us discuss about how do we use inductor and the capacitor in power electronics. Power electronics application. Application of 40 of power inductor and the power capacitor. Okay, well, so he said that so he say power capacitors and the power inductors are used in power electronics to store electric energy, but also this one are used in filtering to store electric energy. Also we are using this in filtering, and there is also power inductor and power capacitor in voltage regulation. Voltage regulation in power supplies. Power supplies and the power converters. Power converters. Example, power capacitors. Are used to smooth and they filter the output signal. The output signal of rectifier. The output signal 40 of rectifiers. Also, we say that this is one of the example. Example 2. Power inductors are used in DC to DC converters. DC to DC converters. So in power inductors are used to store electric energy in DC to DC converters. So operating, listen. We say that power capacitors and power inductors are used in power electronics to store electric energy. Say to store electric energy. But also power inductors and power capacitors, especially power capacitors, are used in filtering. Say filtering. Say filtering. So filtering what? We'll discuss in this in the example 1. And also power inductors and power capacitors are used in voltage regulation. Say voltage regulation. We have voltage regulation, and also you have current regulation. I say this, sit down. And then this filtering circuit or voltage regulation, in most cases, when you say the storage of electric energy, the filtering circuit or filtering system, and voltage regulation, we are mostly use them in power electronics whenever we are designing power supplies system. So these explanations about the applications of power inductors and capacitors in OT power the applications, they use the applications of power inductors and power capacitors. So example 1, we say that power capacitors are used to smooth. Say smooth. Say smooth. Say smooth. To smooth and filter the output signal. The output signal of what? The output signal of the rectifier. So we discussed about rectifier at the first power electronics device. So the output of rectifier is not a clear or it's not a pure DC signal. We call it pulsating signal. So that pulsating signal, it contains some of the AC components and some of the DC components. And then we say that power inductors are used in DC to DC converters, where we are focusing on voltage step up and voltage step down. Are we together? So these are the use. So let me support this information with a block diagram there, because electronics is all about drawing. And then I will give you the important announcement, all of you. Let me show you, or let us draw the block diagrams of linear power supply and show you that where we are using the power capacitors. So we say that the block diagram of linear power supply. Linear power supply. So you say that with this block we need the AC main source, just call it AC main. Draw good rectangles and draw by using a pencil AC mains. And then we have another block. We have to draw blocks first. We have something we call the electronics blocks or block and the block diagram. So this is the second block. And at this point we have also a steady block. This is correction of question number 3, test 1. Then we have again the fourth block. And then we have the fifth block. Then we have block number 7. Number 6. So let us label, let us interconnect the blocks. This is the power signal from AC main to the second block. Power signal from the second block to the third block. Power signal from the third block, the fourth block. Power signal from the fourth block to the fifth block, and power signal from the fifth block to the sixth block. Let us label the blocks. This is step down. Step down transformer. Step down transformer. Say step down transformer. Say step down transformer. And this is rectifier. A step down transformer, it's not a unit. It's just a step down. Then you have rectifier. Rectifier. Rectifier unit. This is the unit because it consists of more than one component. Then you have filtering. Filtering or smoothing unit. Filtering unit. Then we have voltage regulation. Voltage regulation unit. Then you have loads. And this we call them DC loads. So this is figure 1. The detailed block diagram of a AC to DC linear power supply. Stop writing, stop drawing. I will not write. What am I going to explain? So just listen and ask questions if you do not understand. Say block diagrams of linear power supply. Within this power supply, we have some power electronics parts. This is AC mains. AC mains, we actually need a AC socket and the AC power cable to take the current from AC extension or from the socket towards the step-down transformer. And then in this block, the step-down transformer is not an electronic component, it's an electrical component. And this step-down transformer, in case of the because we have 220 volt to 240 volt. So the step-down transformer can step down 220 240 volt to different range. It can step down from from 60 volt up to 24 volt. Then the output of the step-down transformer will be fed to the rectifier. And rectifier units we are going to use either to 4 PN, it means we are going to use either half-wave rectifier, full-wave rectifier, and bridge rectifier. So the bridge rectifier, it has so many advantages compared to the half-wave rectifier and full-wave rectifier. So for this part, we are going to use a full-wave rectifier, a bridge rectifier, because there are so many advantages compared to the other two types of rectifiers. One day you may be asked that, why do we use bridge rectifier in designing linear power supply? Then, after that, so we have also two options. We may use a bridge rectifier integrated circuit, either through hole, bridge rectifier integrated circuit. Or you can have a surface mounting device or SMD device, bridge rectifier. Are we together? Are we together? Yes. Or you may also use a 4 PN junction diodes. You may buy a bridge rectifier IC, or you may use 4 PN junction diodes to design the bridge rectifier. So that is all about power electronics. Then today I add something in your mind. Previously, when I drew these block diagrams in lecture 2, I told you that in lecture 2, yes, it was lecture 2. This is the power electronics block, or this is the block where you have power electronics, because by that time I was teaching about diodes. I didn't teach you anything about power capacitors and power inductors. Where? So, from this discussion, or from example what? From example 1. Power capacitors, say power capacitors. So I use it to smooth. Say, I use it to smooth. And filter the output signal of 40 of 40. So this filtering unit, we are just using power capacitor. Smoothing, remember that theoretically we say that a diode converts AC into DC. Practically, a diode converts some AC components into DC components, but it fails to convert all the amounts of AC which has been supplied to its input into DC. And that's why that we need some other blocks before we deliver the output to the loads. Are we together? So filtering unit or filter unit, either filter units or filter units, this is another block of power electronics. So in lecture 2, I just told you this. Today I'm adding value. Okay? Because here we are just using electrolytic capacitor. And there's a difference. If you disconnect that electrolytic capacitor, you ignore it. I want to tell you that you won't get the DC that you intended. Are we together? Are we together? Class, is it clear? Ask you questions about what we've discussed about power capacitor and power inductors. It's your responsibility now to go and think about the block diagrams where we are using power inductor. So you said power inductors are used in DC to DC what? Converters. Are we together? DC to DC what? Eh? Yeah. So remember that in these entire systems, it doesn't mean that all the parts are the power electronics. No, some of the parts are the power electronics. In test 1, I just asked you that to draw a detailed block diagrams of linear power supply. This is the response. And explain one block of power electronics. For that questions, because I did not teach you about filtering unit, you just have to explain how does rectifier unity work in this system. That's all. Unfortunately, a number of students, more than 70%, they have been explaining each block. Who asked you to explain each block? Read question clearly and understand. Ask a question. Is it clear? Pardon? Can you repeat your question? Deborah did not hear your question.
You say capacitor. Voltage regulation.
Okay. So he said that according to this explanation, we are using power capacitors and power inductors in power electronics to store electric energy, filtering, and voltage regulation. So his question is, how about this block? It is a power electronics block? That is his question. And the response, this is not a power electronics block. Why? Because in voltage regulations, we are just using integrated circuit that consists 18 bipolar junction transistor. So when you talk about voltage regulation, it doesn't mean that, listen, my dear students, when you talk about voltage regulation, we have different electronic systems which consist in voltage regulation. This is one of them. Okay? So we mentioned voltage regulations, and the intention, we don't mean about voltage regulations in linear power supply. No. Voltage regulations in other power supply system. Okay? Another question? Another question. I'm waiting 3 questions from you. Otherwise, we'll never end this class. I'm waiting because you don't ask a question. When I ask you a question in the exam, you fail. So it's a time for you to ask a question about what you've been discussing today. And some students used to lie to me. Sir, we have questions to ask because you have answered all the questions during your teaching. And that's the lie. So talk to your neighbor. Which question should we ask? First of all, is the concept clear? Eh? Don't think to ask you many questions about how is it working. No, no. This is brief. We are still discussing, or I've just given you the high level overview, the general overview, not detail. So think about that general overview. What questions would you like to ask so that I can answer and you can get more information? It's very surprising to teach more than 50 students and none of them who has a question. It's very surprising. For instance, myself, I had my classmates, we are only 53 when we were in first year, but in every class I used to attend, I used to ask minimally 3 questions. In every class, and in each module, because I just wanted to understand. So I used to create questions according to what has been taught. But you, more than 50, I teach lecture. Is it clear? Hey, pa. When you go for the exam, oh, this question is simple, but it's not clear. Okay, David has a question. Ask it.
Which one is more suitable in high-speed switching between SSRs, IGBATs, and styristors?
So which one has a high switching speed between silicon controlled rectifier, IGBT, and what? GTO. Huh? Styrista. Okay, did you hear David's questions? He said that which one has a high switching speed between silicon controlled rectifier, insulated gate bipolar transistor, and styrista. So the answer of that question, Mr. David, it depends to the place or depends to the applications, because the switching speed for SSR, it might be less than the IGBT, but it's important in particular application, where that the speed of IGBT is greater than the one required. The speed of IGBT might be greater than the switching speed of styrista. But IGBT, it has been discovered that its speed is actually compatible in particular system, where that styrista is not compatible. Okay? But all of them have a very high switching speed. But now the level is in case you get into too much detail. To know the switching speed, how is it measured, first of all? How the switching speed for SSR or of these power electronics devices are measured. So once you know the number or the high speed for this one, the highest speed for this one, then we can talk about which one has a high switching speed. Okay? Another question? Okay, so I think that we've been discussing about we've discussed about 3 power electronics devices. The first one is IG. It was SSR, IGTO. No, it is GTO, and power capacitors and inductors. And this is the practical questions. I have just dedicated my students to make sure that to understand or to learn how to design the schematic circuit diagram, also how to perform the simulation, either in PSpice, online or offline. I've taught them different simulation software. But also they have to build these circuits on the breadboard, do the measurements by using digital multimeter, and the SEDI assignment is actual to do the measurements and display the waveform by using digital oscilloscope. So let's say that this is the end of lecture 4. And also it's the end of chapter 2. In the next 3 lectures, we are going to start another topic, which is called the power electronic circuits. And sometimes we'll be just taking one power electronics device and discuss it in detail. So I would like to welcome you in future classes, but let me know, did you understand what you've been learning? Yes. Class, did you understand what you've been learning? Yes. Okay, so it's a time to appreciate you, to congratulate you, get prepared. Get prepared, smile. Smile before your neighbor on your right hand side and left hand side. Tell your neighbor now we reach the end. 1, 2, 3. Ongera. Imara. Wow. Then again. Good. Better. Bessie. Thank you very much. May God bless you. See you in the next topic. Afrika, wabariki